everyone. Thank you for joining. It is my sincere pleasure to introduce our speakers, Tim Sullivan and Chase Lample of Somni Scientific, as well as our own lead application scientist, Dr. Andrew Van Praag from Spectral Instruments Imaging. Today, they will be presenting a webinar on anesthesia considerations in small animal imaging. I am personally very excited about this topic because many of the questions and support requests that we receive from our customers actually have more to do with anesthesia settings than they do operating the actual optical imaging system. So to demystify the process, we gathered a brain trust of experts, both from SII and Somni, to discuss the use of anesthesia with your in vivo imaging systems. And without further ado, Chase, please take it away.
Yeah, good afternoon or good morning, depending on where you're located. We'll look at the agenda. So first, we'll take a look at the methods of anesthesia, followed by animal handling. Next, we'll look at what a vaporizer is and how it works, and then review safety and regulatory considerations. Next, we'll look at vaporizer and delivery systems, and more specifically, active versus passive style systems, and how each of these systems are used to manage or the lack of ability to manage waste gas, followed by system handling, and then a review of the Penta and Deca flow offered by Spectral. And then we'll follow everything up with questions at the end. Methods of anesthesia, just when conducting research, two methods of anesthesia are commonly administered, injectables and inhalants. Injectables are as they sound, injected via intravenous therapy directly into the patient's vein, whereas an inhalant is administered via nose cone, mask, intubation, breathing apparatus, and inhaled by the patient. The goal of both of these anesthesia methods is to sedate the patient. Injectables offer less control and do not provide adequate sedation over long periods, while lacking the ability to meter sedation. When properly used with accurate delivery and scavenging systems, inhalant anesthesia has proven to be the safest and most effective method to administer this life-saving drug, providing a quick, cost-effective method to anesthetize patients for long periods of time. Over time, anesthesia has evolved. The first use of anesthesia was in the 1800s for dental procedures using nitrous oxide. Nitrous later gave way to the birth of ether in the mid-1800s and later halothane in the 1950s. Due to complications with clinical practice of halothane led to the development of new and improved agents that were better for the patient and the environment. All inhalant anesthetic agents require a vaporizer for the delivery and to the animal via a carrier gas. Two of the most commonly used agents today are isoflurane and sevoflurane, also referred to as iso and sevo. While very similar, iso and sevo have slightly different effects and mechanisms of action, even though the anesthetic result is nearly identical. For example, sevo is most commonly used in human use and becoming more popular among veterinary ER rooms due to its ability to quickly sedate the patient while providing a faster recovery time. So, advantages of being dosing level can be readily adjusted as needed and metered and monitored, relatively insoluble in blood, so the ability for the patient subject to recover quicker, and those two things contribute to a lower mortality rate. I'm going to let Andrew speak to some animal handling tips here. So Andrew, if you want to take it away.
Great. So, Chase, thank you for that. The questions that we often get when it comes to animal handling is how to set the flow rates for the anesthesia system and what we should be observing when it comes to the behavior of the animals when they're underneath anesthesia. So therefore, these handling tips. It is indeed, in fact, important to closely monitor the breathing rate that the animals are exhibiting when they're underneath anesthesia. This is one of the primary clinical signs that you'll see in response to anesthetic gas. And for mice, the typical breathing rate that you're aiming for is 1 breath a second. If a mouse looks like it's breathing faster than that, well in excess of 1 breath a second, it is essentially being anesthetized too lightly. And so what you'll want to do underneath that kind of a scenario is gradually increase the percent isoflurane vapor that you're exposing the mice to. So I would suggest a 0.5% increase from where you may start, let's say 2.5%, and then closely monitor the breathing rate of the mice as you increase the percent ISO. once you get back to that 1 breath per second rate, that should be fine. Alternatively, if mice are breathing less than 1 breath a second, if there's like a lot of head snapping that happens as they inhale deeply trying to get oxygen, that's obviously an indication that the mice are too deep. They're being too deeply anesthetized and they run the risk of experiencing asphyxia altogether. In that kind of a scenario, you immediately want to reduce the percent ISO that you're giving the mouse to the tune of about 1%. Remonitor that head bobbing should be replaced by more easily taken breath at 1 breath a second. Now, anesthesia in the form of the inhalable isoflurane is a very light and relatively safe way of doing animal anesthesia. Nevertheless, it does have an effect on the overall animal physiology. Never mind breathing rate, there's the body core cooling that will happen. And the common sense rule of thumb is never to keep a mouse underneath anesthesia for longer than you need to. An interesting aspect of anesthesia is that very similar animals, in fact, animals within the same species, may not respond to anesthesia exactly the same way. For instance, neonate mice and their adult analogs respond to anesthesia in notably different ways. There are various anatomical features and physiologic realities of neonate mice that cause them to actually be harder to get underneath anesthesia. The lack of full pulmonary alveolar glomeruli development and various different changes in blood water content in neonates makes it so that you will have to actually raise from the standard 2.5% isoflurane gas to a slightly elevated rate or concentration. Conversely, in mouse models that you're working with, if you happen to be dealing with something that is impinging on oxygen transfer in the lung, let's say you have an orthotopic lung cancer model, those kinds of mouse models will be more sensitive to the exposure of isoflurane gas, and you will want to reduce from the standard of 2.5% down to a lower percent to avoid asphyxiating the mice altogether. There is also an interesting effect with regard to the pharmacokinetics of drugs and the pharmacokinetics of substrates in bioluminescence imaging scenarios, and I'll focus on that here. So if you are typically setting up the mice to do bioluminescent imaging, and you do injections of the substrate, D-luciferin for firefly luciferase as an example, you will note that the distribution of that substrate is actually quite rapid by comparison to a scenario where you anesthetize the mouse first and then inject the substrate. So the simple point to be made here is that whatever technique you develop, injection followed by anesthesia, anesthesia followed by injection, you always want to maintain a consistent routine, because your peak kinetics for the distribution of the D-luciferin to the luciferase enzyme expressing cell populations will be dependent on it. And you will get peak signal at different time points based on the order in which you do the injection followed by the anesthesia or vice versa.
Great, thank you, Andrew. So what is a vaporizer? The vaporizers are the heart of the anesthesia machine and one of the only life-critical devices. A vaporizer is defined as a device that delivers a given concentration of volatile anesthetic agent. It works by controlling the vaporization of anesthetic agents from liquid and then accurately controlling the concentration in which these are added to the fresh gas flow. The design of these devices, including the Somni 3, takes into account varying ambient temperatures, fresh gas flow, and agent vapor pressure. On the left here, we've got a nice schematic of a traditional Tech 3 style vaporizer. I'd like to walk everyone through this and maybe provide a better understanding of how the vaporizer works. So starting in the bottom right-hand corner where the filler is, the first part of using a vaporizer is filling it with the liquid anesthetic, which you can see here with the filler. The liquid agent is housed in the sump, which contains the helix wick supports and the wicking. The anesthetic agent is absorbed into the wicking, making the wicking design and material a crucial component. Our Somni 3 vaporizers utilize an advanced internal wicking system. This is the same as used in human anesthetic vaporizers today. To start the vaporizer process, a carrier gas, usually oxygen or air, or a mixture of some combination, is introduced in the inlet and traveled into the sump, where the thermostat or the temperature-sensitive valve is also on. The thermostat is crucial for regulating temperature and pressure compensation, and the therm works in conjunction with the rotary valve to provide an accurate vapor delivery percentage at each dial setting. The dial is used as a visual indicator of the percentage of vapor delivered to the patient, and the dial markings are established during the calibration of the vaporizer. So each vaporizer has a unique calibration setting, which the dial should reflect accordingly. Your ISO dials range from 0 to 5%, and the SIVO dial will range 0 to 8%. So once the carrier gas and the liquid anesthetic have mixed in the sump to create a vapor, a combination of the two are delivered through the outlet connector to the patient as a fresh gas. The vaporizer in the anesthesia system can be a main source of waste gas exposure to the operative, and safety and regulatory requirements around waste gas exposure have become more widely recognized globally in recent years. Some regulatory requirements can depend on your state, country, or governing body, and they can vary as such. But waste gas management is something that Somni puts at the forefront of design and development of our equipment. And until recently, the scavenging of waste gas has not been done effectively. It's now becoming a focal point for groups such as the environmental health and safety departments as they're beginning to take notice of exposure levels within their facilities. The NIOSH has a recommended exposure limit not to exceed 2 parts per million over an 8-hour time-weighted average. We always illustrate this with the question, if you can, or can you smell isoflurane or sevoflurane? If the answer is yes, you're being exposed to many 100 times greater than this limit. And we will review several ways to help mitigate exposure to waste anesthetic gas throughout the remaining part of the presentation. One way to combat waste gas exposure is by properly maintaining your anesthesia machine and vaporizer. So if any of the below issues are observed with the vaporizer, it's time to have the equipment inspected and serviced. These can include the control dial is difficult to turn, so you're not able to it should have like a very smooth action to it. The dial turns freely, but there's no agent output, so you're not getting any kind of fresh gas delivery to the nose cone or induction chamber. The vapor percentage numbers on the dial are not legible and are hard to read, so you're not aware of how much percentage vapor you're delivering. Visible leakage of liquid or vapor. This can also be detected sometimes just by the smelling of the agent. Agent discolorization, which can be seen when draining the vaporizer or in the sight glass, if they have one. And then usually most vaporizers will have a sticker on them indicating when service is recommended. So if it's elapsed that time of the recommended service interval, they should be sent in or inspected. So looking at what services are available and how are they performed, there are two methods most commonly used to service and maintain anesthesia equipment. The first one we recommend to all customers is an annual efficacy test. This test can be performed on site and includes the inspection of the vaporizer and an output check at each dial percentage using a Rankine gas analyzer. The second type is a vaporizer service recalibration. This service is more complex and can only be conducted in a laboratory controlled environment. The vaporizer is disassembled, replacing all the wetted parts, including the seals, gaskets, and wick, and then thoroughly inspected and rebuilt as new. Lastly, the vaporizer is calibrated using a laser refractometer, which is the gold standard in vaporization calibration and used in human anesthesia. Performing anesthesia services as outlined will ensure clinical accuracy, operative and patient safety, and maintaining study validation. Additionally, there is a value ROI from continual service from lost agent due to the degradation of seals over the vaporizer's lifetime or having equipment out of commission and not being able to perform studies. Some facilities may notice this by the amount of agent that older vaporizers left unserviced use versus newly purchased vaporizers. We have an internal calculation of savings that can be used by the facility to determine the cost implications and saving if interested. There are some companies out there that will promote that their vaporizers are calibrated for life or try to redefine what a vaporizer is and saying that it doesn't need to be calibrated. But ultimately, if you're using a device that converts liquid anesthetic to a gas, an output test should be conducted annually and service and recalibration biannually. The vaporizer is a pneumatic device. It's a lot like an airplane, so it has Viton seals and Fritox and joints. So like an airplane, we would never get on an airplane that's never been serviced. We would also never recommend using a vaporizer that's never been serviced. So considerations to look at and review when choosing a vaporizer. First, we want to identify the type of agent. So whether that's ISO or SIBO. Isoflurane is probably most commonly used in research. Next, we look at the sump capacity. So we offer both a 125 milliliter and a 250 milliliter vaporizer. We offer the standard Tech 3 vaporizer is 125 milliliters, where the extended capacity is 250 milliliters. We find some customers prefer the extended capacity because it holds an entire bottle of ISO or SIBO. So by default, if it will hold an entire bottle of ISO or SIBO, it's less filling, which offers less potential exposure. Next is the material of the vaporizer. So brass versus aluminum is kind of long been the debate. We manufacture all vaporizers using specific brass and alloy materials, ensuring accurate heat transference and reaction with the anesthetic agents. Unfortunately, due to the lack of regulation in the animal market, other manufacturers have looked at taking the cost out of the vaporizer, but at the sake of the quality. As you can see in the pictures on the bottom left here, these aluminum vaporizers can react adversely with water, cleaning solutions, and agent when in contact. The same external corrosion also can occur internally of the vaporizer, which when mixed with the agent and fresh gas will cause toxicity. Next is the filler type. So there's two common standard filler types, both the key fill and the funnel fill. The funnel fill is more commonly used in the US and North America, and the key fill is widely adopted in the UK and the EU. I personally prefer the key fill as it helps to further eliminate exposure to waste gas when filling, but we provide both options for our customers. If using a pour fill or funnel fill, we can provide anti-spill devices as pictured here on the right. This helps just to control the agent when pouring into the vaporizer. There's also the key fill adapter, which is suggested fits snugly into the key fill slot, allowing the agent to be poured directly into the sump. Next or last would be the carrier gas supply. So we talked about how the carrier gas flows through the vaporizer, interacts with the agent, and then is delivered as fresh gas. The most commonly used ones are E-tanks and H-tanks. If you're lucky enough to be in a new building, you may have quick wall disconnects for in-house air supply. But one that we're noticing a lot of customers are becoming more accepting to and stepping into are oxygen concentrators. They've become very popular for a number of reasons. One, they convert room air into a higher purity oxygen, typically 90 to 95%, eliminating the need to manage E and H tanks. So by default, by eliminating the need to bring in tanks in and out of the facility, it further reduces exposure to potential pathogens into the laboratory, which can be important for immune compromised animals. And then lastly, they're just a greener and friendlier product just to the environment. So also just by reducing the trucking of the tanks to and from the facility, you're eliminating that with having an oxygen concentrator in the room. Next, we're going to take a look at types of delivery systems, and I'll hand everything over to Ken now.
Good afternoon. Today, we're going to talk about a few of the different types of delivery systems you'll see out there. One of the most popular ones you'll see out in use in the labs is shown on the left-hand corner there. Basically, a vaporizer mounted on some sort of a frame with a single flow meter. They're referred to as tabletop units. They're popular because of their portability and size. Typical use of this kind of a system is to use it to deliver fresh gas to one or two devices at one time. A lot of times we'll see the user having one fresh gas supply going to an induction chamber and a second fresh gas supply going to a nose cone. The downside to splitting the gas in this manner is you don't really have any control of how much of that flow rate goes to each device, just the overall flow rate controlled by the flow meter. Another type of system and more efficient is shown on the right-hand side. These types of systems are pressurized systems. The one on the right is the Somni AMD3. The AMD stands for Adjustable Multiple Delivery System. And others like it have multiple outlets that are controlled by either switches or flow meters and switches. So in this unit, you can see there's 3 independent flow meters, so you can precisely control the amount of fresh gas, the flow rate of the fresh gas being delivered to each device. We also include switches to where once you get that perfect flow rate set, you can just turn the switch on and off, and you don't have to reset the flow meter each time. A lot of the systems out there just only have the switches and not the flow meters. So Chase has talked about the vaporizers, the anesthetic agents, and we've gone over the different delivery systems to a certain extent. Now we're going to talk about the other side of the equation, the waste gas, or the WAGs. The waste gas is the unused anesthetic agent that's left over that the animal hasn't breathed or used. So there's 2 methods of dealing with the unused waste gas. One is a passive system, and one is an active system. On the passive system, shown on the right-hand side, the fresh gas pushes through the device, whether it's a induction chamber, nose cone, whatever, and then on through a tube to typically a charcoal filter. The downside to this is the gas always takes the path of least resistance, which is typically not through a small tube and then getting pushed through a charcoal filter, but around any unsealed areas of a nose cone or the induction chamber, especially when you open the induction chamber to bring the animals in and out. So there's quite a bit of exposure trying to use a passive system. What we recommend is an active system. The active system actively draws away the waste anesthetic gas. It's a far more efficient way to contain and control the gases. A good example of this active system is you can see with the induction chambers shown in the photograph there. On the left, we have the active system, on the right, the passive. The passive style on the right has a fresh gas supply coming in at the bottom and the gas going out in the second outlet just above it. Your fresh gas supply is coming in at 2 liters a minute, so there's a 2-minute flow rate flowing out of the upper port also, which is being passed through a small tube and into a charcoal filter. This creates back pressure, forcing the anesthetic gas out the top of the chamber as soon as you open it, exposing the user. The active chamber on the left-hand side has the same port feeding into the bottom of the chamber, but as you notice, the port is moved up above the lid, and what we do is actively draw away the anesthetic agent. So there's holes in the lid, so you're not building up any back pressure inside the chamber. It's escaping out through those holes and being drawn away by an active system of some kind. So there's different types of active systems. One of the types is an in-house vacuum. Now, if the facility has an in-house vacuum, that's great. The thing you have to be aware of is you have to attenuate that negative flow. Most in-house vacuums have too strong of a negative flow to apply directly to different devices. So it has to be attenuated with a flow meter of some kind. Another system that is used in facilities is a snorkel type system. It's typically a large flexible hose with a negative flow created by some kind of a suction fan, in-house suction fan or something. The snorkels work fairly well, except you have to be pretty close to the snorkel to allow for the waste gas to be drawn away efficiently. And if you're too close, then it can also draw away too much of the anesthetic agent. It also limits your workspace and placements of the devices because they have to be near the source of that snorkel. A downdraft table or fume hood is another system that we see in some facilities. It is also way better than a passive system, but it has its downsides. When you're working on top of the downdraft table, you're actually restricting the negative flow in that work area. And it also, again, you run the risk of drawing the anesthetic away from the animal if that downdraft is too small. There's also some smaller systems that are ran off of a fan. Typically a squirrel cage fan creates a negative flow. The downside to these systems is you don't have any control over that negative flow. The farther away you are from the fan source, the less that negative flow becomes. Also, as you go through longer lengths of tubing, it also reduces that negative flow. So our EPS3 system, shown in the top there, is basically a miniature in-house vacuum unit. So we've incorporated a built-in linear vacuum pump that creates up to 60 liters a minute of negative vacuum. This negative vacuum is precisely controlled through 3 independent flow meters, giving the user the ability to get the precise amount of negative flow needed for each device. Different devices are going to need different amounts of negative flow applied to them. An induction chamber is going to use quite a bit more than a nose cone. So adjusting this negative flow is pretty important. We also supply this unit that doesn't have the fan, and it can be used to hook to an in-house vacuum unit and be used to attenuate the in-house vacuum unit's negative flow and give you the precise control needed. Next, we're going to talk about the waste gas canisters. All waste gas canisters are not created equal. There's some design flaws in a lot of these waste gas canisters. One of the biggest flaws is a lot of them bend out the bottom. The problem is anesthetic agent is heavier than air, and it just continues to leach out the bottom even if after you collect it. The other problem that we see is the user will set these filters on their side because you can't stand them up or you block the ports. And then it just channels across the top, so the charcoal's not really accomplishing anything. So we've designed a filter a little bit different. It has a down tube design. So we take a down tube and take the waste anesthetic gas to the bottom of the canister, and it has to work its way back up through the activated charcoal. This allows the activated charcoal to do its job and collect the isoflurane molecules going up through it. The quality of the activated charcoal in these different filters also make a big difference on the efficiency of the canister. As you'll notice, the size is also important. The smaller canisters shown on the left-hand corner there, they absorb around 50 grams of gases. Ours absorbs 200 grams. So it doesn't have to be changed nearly as often. The larger size also allows for a greater airflow to go through it. And there's plenty of charcoal in there so it can still do its job. These little fan-based systems with the charcoal sitting filter on top of them, all they're doing is drawing that air at a pretty rapid rate through the filter and just scattering it, all over the room. So it really doesn't work all that efficiently. Andrew, do you want to chime in here?
Well, let's see if we can see the overall system. That would be great. So as a user of the Somni AMD3 and EPS3 system, this is how I normally see it. And it's really a very capable system in the following sense. As Tim has gone through in detail, I will summarize. You have 3 lines of supply and 3 lines of evac. You can set the flow rates as you wish. And then once they're set, you can use the flip switch to basically turn them on and off on the supply side. And the additional thing that's neat about the setup here is it's all color coded. So typically the way you would do the install is that you would have the supply side with the red line going to the induction chamber. The orange line would go to any kind of desktop or lab bench units that you're going to be using, single mouse, multiple mouse nose cone. And the third yellow line that you can see there heading off to the left, in our case, being from SI imaging and using optical imagers, would go to the imaging station. All of the evac lines are blue, and they very clearly designate that way that they're functioning in an evac capacity. And you can see in the case of the induction chamber, we have the large hooded induction chamber where it is using the evac, active evac setup above the perforated lid. And you also have a blue line going off to a lab bench unit, and then off to the left, a blue line coming from the optical imager. So Chase, if you can go to the next slide. So just by way of example with things that I know, we use the Somni AMD3 EPS3 system with our LogOX imaging system. And the thing that I want to get across here is the things that you really do have to know about your anesthesia system when you're using it with an optical imaging station like the LogOX. So the primary thing to be able to set up is a relative flow rate. This is actually very important because the right flow rate will keep your animals fully anesthetized, maintaining a local anesthetic gas exposure without causing that gas to spread across the lab benchtop or to be pressurized out of the induction chamber or to spread throughout the imaging cabinet of your imager. So what we have demonstrated empirically is that a 1:5 ratio, and this can be confirmed by smog testing, where you can actually see the gas pass through the manifold, that a 1:5 ratio of supply to evac will create a nice dynamic equilibrium where you have a small cloud of isoterrane vapor and the continued evac of that so that it doesn't spread. And this also has the very important function in the induction chamber of keeping any kind of investigator exposure to less than the USA NIOSH criterion of 2 parts per million at max. So what's an example in the LogOX system of exactly what liters per minute you would be using in your flows to and from the induction chamber, the imaging system, and any kind of benchtop manifold setup, which I'll exemplify by showing the pentaflow momentarily. The answer to that basically is that with the induction chamber, you're going to want to use something on the order of 2 liters a minute supply with a 10 liter a minute evac. And that's actually twice the flow rate that you'll see recommended for the imaging system and for the benchtop manifold. The reason for that is that you have to fill up a volume of air that is significantly larger in the induction chamber. And if we can go to the next slide, that's exemplified here, where when you're using an active large induction chamber as provided by Somni, you're dealing with a 11.5 by 6 inch space. And that takes some time to fill. So we recommend using a 2-liter supply and 10-liter per minute evac to rapidly create a nice dynamic equilibrium in the induction chamber. And given that there's less space that you need to fill, the mouse nose cone, either on the benchtop unit or in the imager, the flow rates for supply and evac on those two setups is 1 liter a minute supply, 5 liter a minute evac. If we can have the next slide. This is an example of a benchtop unit that is provided to our customer base through Somni, known as the Pentaflow. And the thing that is really neat about this is that you're able to basically have as much space as you need to manipulate your mice while you're prepping them for imaging. So what you can see here in this image is basically 5 mice that are underneath isoflurane anesthesia that's been delivered by the orange line and evac'd by the blue line. And they're all being kept warm by a heat pad at 37 degrees Celsius. Okay, so the way this works is that the manifold tray that the mice are resting on is connected to the docking station, which you can see the supply and evac lines connecting to. That connection is done by rare earth magnets, and it basically will compress and activate a Schrader valve to allow for gas supply and evac. Now, you simply have to hold on to the handles there on either side. As you can see, the investigator has pulled away the manifold tray and is now connecting it to an analogous docking station inside the LOG-OX imager. And again, here you have rare earth magnets compressing the Schrader valve that will then activate the supply and evac of anesthesia. And this basically obviates the need to squeeze inside the optical imager with your hands and position the mice as you need. It also provides the luxury of being able to do whatever kind of therapeutic drug, or in the case of bioluminescence imaging, bioluminescence enzyme substrate injections, all on the lab bench, all underneath controlled anesthesia. What we just now see below the Pentaflow is a further expansion of the same concept, where you can do 10 mice at a time imaging, and therefore the name Decaflow. And the thing that's nice about both of these systems is that you are given 2 manifold trays. All right, so 1 manifold tray can be used to image 5 mice while it's inside the imager in the case of the Pentaflow, or 10 mice in the case of the Decaflow, while you have another manifold tray that is outside on the lab bench being used by the investigator to prepare another 5 or 10 mice, depending on what system you have. So at best, you have a 20 mouse at a time workflow set up through the Decaflow, which is really state of the art. Back to you, Chase.
Yeah, thank you, Andrew. So it was a great review of just the system itself, as well as the Penta and Decaflow. So recapping on ways to ensure your waste anesthetic gas scavenging system can help reduce exposure. First, we want to confirm that the evac system, whether that's in-house or portable, uses a linear style vacuum. We want to be applying a suction via a vacuum versus a downdraft cable or a fan that's used to blow the waste gas. This will help to ensure that the gas is being trapped. We prefer to have a vacuum rate of greater than 45 liters per minute when using multiple devices. This allows adequate suction to the induction chamber, manifolds, or nose cones while conducting imaging or surgery. It's also beneficial just for areas that might have a higher throughput with the amount of animals that they're working on. Second would be to confirm your system has independent flow meters for each scavenging port so that you can accurately attenuate how much gas is being drawn away. And then lastly, just confirming your anesthesia accessories that we talked about in this presentation, whether that's the nose cones or the induction chambers, that they are compatible with an active style scavenging system. If you're using a passive style accessory, they will not be as effective, and you may under anesthetize the animal or over anesthetize them, depending on if you're having to turn up the amount of agent that you're delivering. So Somni is happy to help evaluate your systems and how they're set up. We can help look at the application and then make any recommendations that may be better suited to your system and how to kind of mitigate and reduce exposure to waste anesthetic gas. So with that, that kind of concludes the presentation today. So appreciate everybody's time.